Hello everyone, welcome back to part 4 of Deep Learning with Python and Keras. And today we're going to look at convolutional neural networks, which are specifically used to perform vision-related tasks. So let's get started. So we have our code that was used to detect digits from the MNIST dataset. And these only use dense layers. So in this video, we're going to look at the conv2d layer, which is for convolutions. So from Keras.layers import dense, input, flatten, and now what you want to import is conv2d. You also want to import another layer, and that layer is called max_tool2d. Now all we need to do is that we have to replace our flatten statement with a conv2d statement, because conv2d does not accept just a 1D vector of numbers, but instead it accepts a width times the height times a number of channels of a NumPy array. So you have to make sure that you have as input a NumPy array that has a width and the height of an image, and then the number of channels in this image. And the number of channels in a typical color image is 3. So 1 for red, 1 for green, and 1 for blue. But in our case, since we're doing the MNIST, we only have black and white. So we're just only going to use 0 to indicate black and 255 to indicate white. So we only have one channel. So the width is of 28, the height is of 28, and the number of channel is of 1. So we delete our flatten layer, and now what we want to say is that we want to say that a conv layer is just equal to conv2d. Conv2d of what? Conv2d of in layer. Here we have to define the number of filters, which I'm all going to explain later. So let's say we define 32 filters, and then we select that we have a kernel size of 3 by 3. Again, I'm going to explain this after. So conv2d 32, 3 by 3, kernel size of 3 by 3. And then I can say that the activation is equal to relu. So conv2d 32, 33 activation equal relu. Now, if we want to add a dense layer after, we have to make sure that we flatten it, because as I've said before, dense layers only accept one-dimensional NumPy arrays. However, the convolutional operation will return a width times height times channels image. So what we can do is that we can just say flatten layer is equal to flatten what? Flatten conv. So all I need to do now is I can just change the number of epochs, just say to 5 because we just want it to run faster. And now I can just say python main.py. And we all have to wait. So we see our beautiful digits that we printed. And now it's time for the epochs. So I have failed to get convolution algorithm. This is probably because cuDNN failed to initialize. So try looking to see if a warning log message was printed above. If you ever have this error, what I usually do to fix it is that I use something that I found online. And what you have to do is that you have to import OS, and you have to say os.environment for environment tf force GPU allow growth is equal to true. And this magical line will make your code run if you have the same error as me. So fail to get convolution algorithm and all this stuff. So if you ever have cuDNN fail to initialize as error, but for GPU users, all you need to do is to put these two magical lines and then it's going to work. So let's run it again, python main.py. And now we wait as usual. So we see our beautiful digits. And now you see successful, everything seems to be working. And now you see that's training. So again, I'm going to show you the line. It's import os.environ tf underscore force underscore gpu underscore allow underscore growth equal to true. And it's just going to set up the environment variable tf force gpu allow growth to true, and then TensorFlow or Keras will see this and it will change it accordingly, and voila, it will make my stuff work. So already we see that at the first epoch, MNIST already gets 98% accuracy compared to the dense layer that has 97% accuracy. And as you can see, it just keeps getting better, 0.9842. And if I remember the results correctly from our dense layer only, what it was that it was like 9822 or something like that, not as high as 9868. And now you see it keeps augmenting. So convolutional layers are especially suited for vision related tasks. So if you put an image and you want to do deep learning, you have to use convolutional neural networks. So we've seen how convolutional neural networks works. All you need to do is that you have to say conv2d, the number of filters, the kernel size, then activation is equal to what, and then in layer. Also, what I'm going to do right now is just present something that's more typical of a convolutional neural network. So we're also going to include the max pool 2D. So to do this, I have to say pool is equal to max pool 2D. And now, all I need to say is that I put conv. Now we have conv equal to this and pool equal max pool 2D conv. And now, all I need to do is change the input to the flatten to pool. But actually, I'm not finished yet. I want to add another convolutional layer. So, let's just overwrite our variables. Doesn't really matter. Conv2d 64 3x3 activation equal relu. And then what we want to do is that we want to pass in pool. Now, we just need to make sure that we pass a specific argument called padding. And what does say padding is equal to same over here, and padding is equal to same. What this will do is that if you give an image as 28 by 28, the image is going to output, it's going to have 32 channels, this is the number of filters, and then it's going to have the same dimension, so 28 by 28 instead of what it usually does. So it will have less than 28 if you don't put padding equals same. So something that's very unfortunate about that is that if you keep applying conv2d too many times, it's going to reduce the dimensions such that it just becomes 1, and then when it becomes 1, you can't go down to 0, to an image of 0 width and 0 height, and then it'll raise an error. So in that case, I always put padding same to my convolutional layers. We can again overwrite pool. So pool is equal to max pool 2d conv. Now we just need to pass in pool to our flattening layer, and this is a more typical architecture for a convolutional neural network. Okay, so now I'm back on the board. So we were talking about the kernel, and the kernel is just, for us, a 3x3 matrix of numbers that it can be negative or positive. So let's say, for example, we have this kernel that is a matrix of 3x3. So 3x3 numbers, so -1, 1, 1, 0, 0, 1, 1, -1, 0.5. Then we'll have 32 different versions of these 3x3 matrices, and the 32 comes from the first argument we've passed to conv2d, which was the number of filters. So let's say I have these sample images. This sample image which just kind of looks like nothing at all. So just 1, 1, 1, 1, 1, 1, 1, everywhere except for here. And then what I'm going to do is that I'm just going to take the first 3x3 region that I see, so in the topmost left corner. So here I see that it's only 1, 1, 1, so this one. And then I'll see that I'll have to do an element-wise multiplication. So 1, 1, 1, 1, 1, 1, 1, element-wise multiplication with the kernel. So minus 1, 1, 1, 0, 0, 0, 1, 1 minus 1, 0.5. And then this gives us a matrix, and when we sum it all, it gives us 2.5. So now we have to do the second 3x3 region that we see, and it's the green one right here. So 1, 1, 1, 1, 1, 1, 1, 0, 0, 0. So then we just need to do our element-wise multiplication again, and we'll see that we get as an output 2. And so the output convolution will look something like 2.5, 2, and then some other input from the 3x3 element-wise product, and down below it's still going to be some other element-wise product. So you can see that we'll have a square like this, then like this, and then like this, and then like this, and you get it. So this square, it's just like it goes from here to here, then here, then here, and 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 here, here, and so on, and so forth. So the output convolution will just look like something like a 4x4 matrix. So the problem here is that the output from a convolution reduces the size of the image, and in our case, it reduces the size of our image by 2. So the problem with that is that if you perform a lot of convolutions on an image that is of low resolution, when you've performed too many convolutions, it's going to have like no more width and normal height, and then it will raise an error. So when you are at a 1x1 image and you want to fit a 3x3 kernel, it doesn't really make any sense anymore, so it raises an error. So what is the solution? The solution is that we pad the image with zeros on the border. So right now, as you can see, I add zeros in the border, and now I have this additional square as well as this additional square. So I have 2 more squares, and so now we have a 6x6 output. And so we've managed to keep the dimension that we wanted. Now, since we have 32 filters, you can assume that the same thing happens with 31 other filters. And so what we're going to get as an output is that we're going to have a 6x6, and then imagine that you'll have 32 of these that are going to be all different. So for mask pooling layers, all we need to do is that, let's say we had our matrix, and then we'll just say like 2, 1, minus 1, 3, 5, 4, minus 3, 2, 1, 0, and all this. Let's just say I add another 6 right here, 6 and minus 3. Then the max pooling layer is just going to take over each 2x2 squares that it sees, and then move by 2 squares. So what do I mean? So it's going to take this square first, 2, 1, 4, minus 3, and take the max. So it's going to write a 4 right here. Then it's going to move by 2 squares. So right here, minus 1, 3, 2, 1. The maximum is of 3. And now it's finally going to take 2 squares again here, and it's going to take the maximum. In that case, it's 6. Then you can see that it's going to continue on with these numbers here, and these numbers here, and these numbers here. And it's effectively going to halve each dimension that we have, so the width and the height. So we have the 6x6 image. When we perform max pooling on it, it's just going to give us a 3x3. And this is very useful because it allows us to reduce the size of data you need to represent as you go down and down in the neural network. So this just makes it that the image is able to be stored in your model as it gets progressively smaller and smaller. So that was all about max pooling. So I think that's pretty much all I need to say about convolutional neural networks. And then we can just rerun it, and then we'll see if our score gets any better. So again, we have this output. Let's run it, and we wait. So let's drink some water. I hope that this time it's going to perform better. Wow, so this is a first. So as you can see here, the accuracy is of 0.96, but the validation accuracy is of 0.985. And whoa, the validation accuracy here becomes 0.99. So we see that for convolutional layers, it increases the accuracy a lot more. So we got 1% more. So this may not seem a lot, but this is actually a lot, because no matter what dense layer you had, it would be very hard to just as easily get 99% validation accuracy. And also, since MNIST is a pretty easy problem, it's kind of hard to see the difference between a 98 and 99. But if, for example, we take more difficult problems, such as detecting doodles, then you'll see that convolutional algorithms, convolutional neural networks really help a lot. So we get a final validation accuracy of 9 1/8. So as you can see, when we stack more convolutional layers together, it gives us a greater accuracy. And if we compare to before, here we just had 9863 with one convolutional layer, and here we have convolutional layers with max pool 2D, and we get 0.918. So that was all about convolutional neural networks. Thanks for watching. If you like this content, like, subscribe, do all that good stuff. And in the next video, we're going to learn how to use our model into the web. So how we can just drop a number on the web, and then our model in Python can detect it. So stay tuned.